Alright, today I'm gonna do the intermediate machine learning course on Kaggle. Then after that I'm gonna finish watching the relativity playlist. I don't think I'm gonna finish this course today because it says 4 hours there. We're gonna do around 2 hours or maybe 1 hour, something like that. I think this one is. Let me see if the switch is working. Yeah. So welcome to Kaggle's intermediate machine learning course. As some background, machine learning, you'd like to learn how to quickly improve the quality of your models in the right place. In this course, you will accelerate your machine learning expertise by learning how to tackle data types often found in real-world data sets, design pipelines to improve the quality of your machine learning code, use advanced techniques for model validation, cross-validation, build state-of-the-art models that are widely used to win Kaggle competitions, like XGBoost, and avoid common important data science mistakes, leakage. On the way, you apply your knowledge by completing a hands-on exercise with real-world data for each new topic. Hands-on exercises use data from the housing prices competition. Prerequisites: you're ready for this course if you've built a machine learning model before and you're familiar with topics such as model validation, underfitting, overfitting, and the first. If you're completely new to machine learning, go to the first course. That's first exercise already. I've also managed to install Manning, and I'm not completely sure if I did it the correct way, but at least it's showing one of the basic introductory animation they told you to do. It's saving the animation. So hopefully I can start working on that in the future. Maybe after I finish the playlist. If not, OS paths exists, OS links. So this is just getting the path, I think. And then the other libraries for machine learning. So this is the data set for the house pricing competition, which is a beginner competition. So I assume this is the data set for the full thing, and then this is the data set for the test. Obtain target and predictors. So the target is the sale price of the full one. Futures is the columns that is gonna test. And it's creating a copy of the next full, next test. Break off validation set from training data. Train size. So I assume this is making 80% of the data set as a train size and 2% as the test size. And random state, so it's equal over time. Or so is distributed randomly across the two data sets. The next cell to print the first several rows of the data. So next code cell defines 5 different random forest models. Run this code cell without changes. To view random forest, look here. So this is the one that I used on the last tutorial. It's not running. To select the best model out of the 5, we define a function score model below. This function returns the mean absolute error, the validation set. call it the best model will obtain lowest mean absolute error. So random state, mean sample split, next that. I kind of forgot what an estimator is. I think it's the parameters. I'm not really sure. Maybe it's a hyperparameter. Run the code so without changes. What? Oh, sorry. Accidentally collapsed that. So this function gets the model, x and y for training and validation, then fits with the test, makes the prediction model with the x validation, which is gonna give the prediction for y using the test. The after it fits the model to the test to the training set, it's gonna use the x to test it and return the error, which is this function calling the y from validation against the prediction from the model. For I in range 0 length models, then it's calling the function on a loop. And models is this list with all the models. So the lowest one seems to be the fifth, no, the third one. Evaluate several models. Use the above results to fill in the line below which model is the best model. So I think it's model 3. Generate test predictions. Great. You know how to evaluate what makes an accurate model. Now it's time to go through modeling process and make predictions. In the line below, create a random forest model with the variable name my model. So forest regressor. I think that's how we do it. That's correct. Run the next code cell without changes. The code fits the model to the training and validation data. Then generates the test predictions that are saved to a CSV file. These test predictions can be submitted directly to the competition. So it's gonna fit with X and Y, then creates the prediction based on X test, and outputs the prediction. And it seems that is not comparing the true the prediction with the Y validation in this final step here. Don't know why. Still thinking about what I'm gonna do first. Uh, because there's other things that I need to do besides. I was thinking about after I finish this
Now that we have
playlist to start the other one from this channel and start coding using many the stuff that I learned to make it more fixed in my brain, let's say. But that's probably gonna take a long time, and I'm not sure if there's other things that I need to learn first. I was thinking about there's just a lot of stuff that I have to think about and try to put it in code format. I think what I essentially want to do is build a library of all these essential equations and concepts from a bunch of different areas. So each time I have an idea, I already have everything set up so I can put these things together and make simulations of them. I think that's the best way to go about it, but I'm not sure the order of importance on that. And I'm also learning the Twitter API, which is very confusing. So yeah, I have to think about that. So I think I can close this tab here. Oh, there's also blockchain as well that I need to learn. That's another thing that I ended up not doing from before. So yeah, in this story you will learn three approaches to dealing with missing values. Then you'll compare the effectiveness of these approaches on a real world data set. There are many ways data can end up with missing values. For example, two-bedroom house. I think this was covered on the Kaggle pandas course. A simple option: drop columns with missing values. Just drop an A, I think. Method. Better option: imputation. Imputation fills in the missing values with some number. For instance, we can fill in the mean value along each column. The inputted value won't be exactly right in most cases, but it usually leads to more accurate models than you would get from dropping the column entirely. An extension to imputation. Imputation is the standard approach and it usually works well. However, inputted values may be systematically above or below their actual values, which weren't collected in the dataset. Or rows with missing values may be unique in some other way. In that case, our model would make better predictions by considering which values were originally missing. This approach we input the missing values as before, and additionally for each column with missing entries, the original dataset, we add a new column that shows the location of the inputted entries. So it's replacing and then creating a new column that is showing you which ones were replaced. In some cases, this will meaningfully improve results. In other cases, it doesn't help at all. Example. In the example, we work with the Melbourne housing dataset. Our model will use information such as the number of rooms and land size to predict home price. Don't focus on the data loading steps. Instead, you can imagine you're at a point where you already have the training and validation data in X-training, X-validate, all this stuff. Define a function to measure quality of each approach. Define a function score data set to compare different approaches to dealing with missing values. This function reports the mean absolute error from the first model. Score, score from approach 1. Drop columns with missing values. Since we are working with both training and validation sets, we are careful to drop the same columns in both data frames. So first is looping through the columns of xtrain. If xtrain is null, dot any. So if there's any value, it's gonna be attached to this variable here. Drop columns in training and validation data. Reduce xtrain equals xtrain dot drop. Then the variable x is determines that is column. X is equals 1. It's for columns. So it's creating a variable with all the null values and dropping. But it's dropping the entire column, I think, here. Score there, reduce. Score from approach to imputation. Next, we use simple imputer to replace missing values with the mean value along each column. Although it's simple, filling in the mean value generally performs quite well, but this varies by dataset. While statisticians have experimented with more complex ways to determine inputted values, such as regression imputation, for instance. The complex strategies typically give no additional benefit once you plug the results into sophisticated machine learning models. So simple imputers model from sklearn apparently, and I think I've used this as well on the housing regression project, and replaces the new values with the mean value. So I have to call fit transform xtrain. So first you fit on the train, then you call transform on x value. You fit on the training and then replace on the validation. Validation removed column names, put them back. Put that x train dot columns equals x train dot columns. See that approach true has lower MA than approach 1, so approach 2 performed better on this dataset. Score from approach 3, extension to imputation. Next, we input the missing values while also keeping track of which values were inputted. So this is a little bit more complicated. Let's create a copy of both of them. So make new columns indicating what will be inputted. Column calls with missing. Where's calls with missing? I think it's the first variable that was created there. Here. So calls with missing is the columns with missing values. Call plus was missing. So call is, I assume, is the name of the column, of each column. This is the list of the columns that are missing. Call is the name of each column that is missing. And it's gonna make a new column called the column plus was missing. And then it's gonna be equal to the values that are null, to the boolean of the values. If it's null, it's gonna return true, and if it's not null, it's gonna return false. Then it creates simple inputter object and creates a data frame with the fit transform from the X training and performs this transform on the validation. Station removes columns, put them back on. So this method removes the columns and you have to put them back on after that. Not sure if I remember everything exactly, but as you can see, approach 3 performs slightly worse than approach 2. So why did imputation perform better than dropping the columns? Training data has around 10,000 columns and 10,000 rows and 12 columns, where 3 rows contain missing data. For each column, less than half of the entries are missing. Thus, dropping the columns removes a lot of useful information. So it makes sense that imputation would perform better. No exercises. So first set up the thing. It's gonna be really difficult once I get to the advanced course because the amount of things I have to remember starts increasing. So this is gonna load the training set, makes the variables, x full, drop NA. So it's already dropping the columns here. To keep things simple, we use only numerical predictors. Yeah, categorical ones are more difficult. So this selects only the numerical of the columns. Bake off validation set from the training data. Ready to see a few missing values in the first several rows. I don't understand how this is possible if it's removing rows with missing targets. Because x equals x full. And x full drops an A here. So that's not very clear to me. Preliminary investigation. Run the code cell below without changes. So first is printing the shape, number of missing values in each column of training data. And then attaching the number of missing values and printing that. So the shape is this, the missing values are these ones. Use the above output to answer the questions below. Number of rows, 11, 68. How many columns in the training have missing values? 3. And how many missing entries are containing all of the training data? So that's 58, 76, sure, 76, I guess. Yeah, correct. So it's basically just the sum of these values here. Consider your answers above. What do you think is likely the best approach to dealing with the missing values? Replacing them, probably. Because there aren't many missing values, so if you drop the column, it's gonna be too many. You can expect that dropping columns is unlikely to yield good results. Yeah, for obvious reasons. To compare different approaches to dealing with missing values, you use the same score dataset function from the tutorial. So it's basically the function that compares the mean absolute error, returns the mean absolute error. In this step, you will preprocess the data in xstring and xvalid to remove columns with missing values. Set your preprocessed data frames to reduce xstring and reduce xvalid, respectively. Get names of columns with missing values. So now, isn't that the same thing that is done here? Missing value columns. I think is any here instead of some. Then it's gonna be the fit transform thing. Simple inputter. It's probably not correct. No, imputation comes here. So I think first what they want me to do is drop the columns. And validation. The next val. See if this works. No hashable type series. So I know that I'm trying to drop a series and it doesn't work. So I should either loop that, but I think they did it in a different way here. So maybe in the first line I need to make the loop. Yeah, first line is the loop. For some reason I have trouble understanding this kind of loop. I need to practice more of this. So this is iterating over X string columns and only returning values that are new. Columns that have value that are new. Then I should call this variable here to drop string dot drop. Yeah. Oh, I forgot the access. So I think this part is correct. Let's see if this works. Got multiple values. So let's just drop. Because I think drop NA is already a method to get the no values. On the next code cell, about changes to obtain the MA for this approach. So now it's gonna call the function with the reduce X string, which are these variables here. Imputation. Use next code cell to input missing values with the mean value along each column. Set the preprocessed data frames to input a X string, input a X value. Make sure that the columns names match those in X string and X value. So I have to do a simple inputter. I don't know if it goes into a variable. Yeah, my inputter, simple inputter. Then it's gonna be X string, not fit transform. Now I'm not sure. Then I think here is gonna be X well dot transform. So it's fit transform X string. Oh, and it's creating the data frame out of it. So I don't understand why it creates the object here, but oh, that's why it's using my inputter here. So it's not X string here. It's my No, it makes sense. I did the other way around. I'm not sure if this is XO. Yeah, so it's valid, not wow. Fill in the lines below. Imputation removes columns. Put them back. I know it's dot columns, but I don't remember. I think this is xtrain dot columns. I think this is wrong because probably missing something here that I don't remember. So I have to look. No, it seems to be correct. Let's see. Yeah, correct. So this is 18 and this is 17. Which is weird, but it says I did the things correctly, so compare the MA from each approach. Does anything surprise you about the results? Why do you think one approach performed better than the other? I think it's because the values are probably irrelevant to the thing. Or they have a bunch of outliers maybe. Given that there are so few missing values in the dataset, we'd expect imputation to perform better than dropping columns entirely. However, you see that dropping columns performs slightly better. But this can probably partially be attributed to noise in the dataset. Another potential explanation is that the imputation method is not a great match to this dataset. It is maybe instead of filling in the mean value, it makes more sense to set every missing value to a value of 0, to fill in the most frequently encountered value, or choose some other method. For instance, consider that the garage year BLT column, which indicates the year that the garage was built. It's likely that in some cases, a missing value could indicate a house that does not have a garage. Does it make more sense to fill in the median value along each column in this case? Or could you get better just by filling in the minimum value along each column? It's not quite clear what's the best in this case, but perhaps you can rule out some options immediately. For instance, setting missing values in this column to 0 is likely to yield horrible results. Step 4. Generate test predictions. This final step, you use any approach of your choosing to deal with missing values. Once you've preprocessed the training and validation features, you will train and evaluate a random forest model. Then you will preprocess the test data before generating predictions that can be submitted to the competition. Use next code cell to preprocess the training and validation data. Set the preprocessed data frames to final X train and final X valid. Use any approach of we're choosing here. In order for this step to be marked as correct, you need only ensure. The preprocessed data frames have the same number of columns. The preprocessed data frames have no missing values. Final X train and Y train have the same number of rows. Not the same number of rows. So I'm not sure if I understand what they want me to do. And the next code style to train and evaluate a random forest model. So what does that mean? So should I do the same thing that I did before here? Doesn't have space to create the my inputter object. So maybe it's just the copy. No, so let's try my inputter dot fit transform. Oh, I forgot to make them both data frame. They didn't talk about how to replace the values by 0. So this is correct. For the next code, how to train and evaluate a random forest model. So we score data set function above because we will soon use a trained model to generate test prediction. So it's creating a random forest regressor, feeding to this variable, this x train here, and y train. That makes the prediction with the final x value and prints the mean error, comparing both of them. So I'm not sure how to make this fit transform change the values to 0 instead of the mean. Or to the most frequent. Run the next code so to train and evaluate the random forest model. Part B. Use the next code so to preprocess your test data. Make sure that you use a method that agrees with how you preprocess the training and validation data. Set the preprocessed test features to final X test. Then use the preprocessed test features and train the model to generate test predictions in Red's test. In order for this step to be marked correct, you need only ensure the preprocessed test data frame has no missing values. Final X test has the same number of rows as X test. So I need to make the columns equal. I'm not sure. That's what I'm supposed to do. Preprocessed test data frame has no missing values. Yeah, so I think I need to make the number of columns equals to the number of thing. Fill in the line below, get the test prediction. And now it's just random forest dot predict model dot predict uh, final x test. Maybe it's x valid instead. Not convert string to float. So one of the columns is a string, I think. So maybe I need to put it types number here. Data from object is no attributed type. Select the types. Do not convert string to float. Yeah, same mistake. I was giving me. Yeah, I don't know what I have to do. Well, maybe it's just the same thing that I did here, but for the test instead. Correct. Nice. So pretty much I did everything that I needed to do there on the training part. Then the last thing is to fit the test, the X test. Should the should take remove the null values. It's kind of confusing to be honest. Because here you also do it with the validation thing. You fit on the training and then put on the X. Valid. Yeah. This is breaking my brain. Even though I got all the answers correctly, I'm very confused. I guess I'll just keep going. The next code cell without changes to save your results through a CSV file. Submit. Once you have successfully completed step 4, you're ready to submit your results to the leaderboard. You also learn how to do this in the previous exercise. First, you need to join the competition. Sure that save and run all options selected. Oh no, what have I done? I can't go back. Go to the viewer. Oh. This generates a window in the bottom left corner of the notebook. Open in viewer, this brings you into view mode. Page. Output tab on the right of the screen. Maybe it's just this. Yeah, I think that's it. I think it worked. Yeah, whatever. This tutorial you'll learn what a categorical variable is and along with 3 approaches for handling this type of data. Introduction. A categorical variable takes only a limited number of values. Consider a server, so it's basically a category. 3 approaches. Drop categorical variables. This approach to dealing with categorical variables is to simply remove them from the dataset. This approach will only work well if the columns do not contain useful information. Ordinal encoding. Ordinal encoding assigns each unique value to a different integer. This approach assumes an ordering of the categories. This assumption makes sense in this example because there is an indisputable ranking to the categories. Not all categorical variables have a clear ordering in the values, but we refer to those that do as ordinal variables. So ordinal is basically something that can be changed to the numbers based on the frequency. One-hot encoding. One-hot encoding creates new columns indicating the presence or absence of each possible value in the original data. To understand this, we work through an example. The original dataset color is a categorical variable with 3 categories, red, yellow, and green. The corresponding one-hot encoding contains 1 column for each possible value, and 1 row for each row in the original dataset. Whatever the original value was red, we put a 1 in the red column. If the original value was yellow, we put a 1 in the yellow column, and so on. In contrast to ordinal coding, One-hot encoding does not assume an ordering of the categories. Thus, you can expect this approach to work particularly well if there is no clear ordering in the categorical data. One-hot encoding generally does not perform well if the categorical variable takes on a large number of values. You generally won't use it for variables taking more than 15 different values. As in the previous tutorial, we will work with the Melbourne housing dataset. We won't focus on the data loading step. Instead, you can imagine you're at the point where you already have the training and validation data. So it's doing all the basic stuff first. Take a peek at the training data of the head method. Next, we will obtain a list of all of the categorical variables in the training data. Do this by checking the data type of each column. So object is for anything that is a category, not a number. Define a function to measure quality of each approach. We define a function score dataset to compare the 3 different approaches to dealing with categorical variables. So it's the same function as before. Score from approach 1, drop categorical variables. Draw out the object columns with select the type methods. But this is removing the categorical. Oh, I understand. It's just calculating the mean square error if you don't have the categorical values to compare later. Score from approach to ordinal encoder. Scikit-learn has an ordinal encoder class that can be used to get ordinal encodings. Loop over the categorical variables and apply the ordinal encoder separately to each column. So I make a copy of xstring and xvalid. One thing I was having an issue with is understanding how to put them together after you change your categories. Because you do this copy here, then gonna change. Apply ordinal encoder to each column with categorical data. So you create the object just like in fit transform with simple inputter. Call fit transform. What is the object calls here? So object calls is the list of the columns with a categorical value. Yeah, so it's gonna be a list with the names of the columns. There are categories. And it's gonna fit transform the xtrain data. So it's gonna apply ordinal encoder. It's the same logic as before, but it's just changing the columns to the ordinal encoder format. In the code cell above for each column, we randomly assign each unique value to a different integer. This is a common approach that is simpler than providing custom labels. However, we can expect an additional boost in performance if we provide better informed labels for all ordinal variables. One-hot encoding. we use the one-hot encoder class from scikit-learn to get one-hot encodings. There are a number of parameters that can be used to customize its behavior. We set handle, unknown, ignore to avoid errors when the validation data contains classes that aren't represented in the training data. In setting sparse equals false ensures that the encoded columns are returned as a NumPy array instead of a sparse matrix. So I guess the default format is to return them as a matrix for one-hot encoding, a matrix of zeros and ones to specify each category. And this transforms them into a NumPy array. Choose the encoder, we supply only the categorical columns that we want to be on one-hot encoded. For instance, to encode the training data, we supply xtrain object columns. Object calls in the code cell below is a list of the column names for categorical data. And so this contains all of the categorical data in the trained set. So it's gonna be pretty much the same thing, but this time passing these arguments. But the logic is the same. Create a data frame, we call the method, which is an object, and we transform. Yeah, I guess it makes sense to think about like that because in every situation, this is gonna be when you're using a library, it's gonna be a function, a class defined somewhere, which is an object, which is gonna have a variety of functions. So you're always going to call the class first, and then you're gonna specify which function of the class you wanna perform. So for some reason, I wasn't thinking like that. It just hit me now. The logic behind these things, because everything is essentially an object or a class, which is basically a fancy object. One hot encoding, remove the index, put it back. Then you just make the columns equal to the index equal to the index of the original one. Then you drop the columns to remove the other ones. Oh, so that's what you do. After you create a copy and you do perform the one hot encoding, you drop the columns, the categorical columns from the original one, and then concatenate the data frame with the one that is changed. Which are this two here. Which approach is best? Obviously this one. Yeah. No, it's this one. Or no encoding. In this case, dropping the categorical columns one performed worse since it had the highest MA score. As for the other two approaches, since they return the MA scores are so close in value, there doesn't appear to be any meaningful benefit to one over the other. General one-hot encoding approach 3 would typically perform best. Dropping the categorical columns approach 1 typically performs worst, but it varies on a case-by-case basis. Conclusion: the world is filled with categorical data. It will be a much more effective data scientist if know how to choose common data types. I'm gonna go to the bare phone real quick. There's just a lot of steps to remember, but it seems quite easy actually. Just a matter of practice and doing as frequently as possible until it becomes automatic. I think the most difficult part of this that I found so far is actually understanding how the things work behind the scenes. Using the libraries are not is not difficult, but I think what separates a good data scientist from a bad one is the understanding of how the things work behind the scenes, and that's probably uh, what's lacking on solving very difficult problems nowadays. Yeah, I should do more of the epistemological nature of science and data. So the understanding of the laws of physics and the philosophy behind what is the scientific paradigm, what are the underlying assumptions that everyone is making when they build these models. So I think the most important thing to do with the goal of trying to prevent self-destruction in mind is to build the libraries first, maybe. And this is just very difficult because it's very complex and there are many areas involved in thinking about stuff like this. So here is loading the data frames, dropping the sale price column, which is the target one, then making the y equals the target. This is attaching, making a list of the columns that have missing values, dropping the list from the x and from the test, then splitting the test and the validation set. I think the most difficult thing that I'm thinking about is that there might not be a way to solve this from the scientific paradigm to solve the problem of, because I think at the core of the issue is the distribution of power in the world of exponential tech. That's probably the underlying fundamental issue with all the other issues. But the problem is that I can't figure out, because in order to be able to create a perfect strategy that would allow us to not destroy ourselves, so we would need to pretty much determine the future, because that's the main issue that I'm not sure about. I can't think of a way to solve it because it's impossible to predict what innovations will happen out of a result of the evolution of technology. And because the future of the universe might be computationally reducible, then it's impossible to predict and create a strategy of diminishing the risks and making the systems anti-fragile, because there's always a innovation that can happen that can destroy the whole system, that is just unpredictable, like a black swan or something like that. So I think the main question is how do you optimize and get as close as possible with that in mind. And I think it has to do, you probably, the right path is probably to think about the probabilities of things happening. But then is the issue of categories and datasets. Because how do you define the boundaries of each field and information to determine what's the risk? And I'm not sure which way is better to think about this. Maybe there's a way to connect both the neural networks concepts of stochastic gradient descent and the overall holistic view of how everything correlates with itself. But then uh, that makes me think that's probably more converging towards the side of building AGI, and then it defeats the purpose of thinking about how to prevent uh, existential risk. It's kind of like a paradox. You have to build the thing, but in order to prevent destruction from happening, you have to build the thing that's more likely to destruct, which is what you're trying to prevent. That's why it's very tricky. Notice that the dataset contains both numerical and categorical variables. You need to encode the categorical data before training a model. To compare different models, you use the same score dataset, so it's the same function from all the other ones. The guess the mean, absolute error. It's weird to me that they don't have this function on the library as well, if it's used very often. But maybe it's because this n estimator changes every time, depending on the case. Drop columns with categorical data. You get started with the most straightforward approach with the code sublow to preprocess the data in xtrain and xvalid to remove columns with categorical data. The data frame should drop x respectively. So now I have to remember how to draw. So I think it's pretty much the X string you selected the types and number, but I'll have to look at it. Yeah, exclude object, which is the same thing as selecting number, I think. But I'm gonna use this for now. And then it's the same thing here, correct? Now the calculates the MA using the function. Before jumping into ordinal encoder, we'll investigate the datasets. Specifically, we'll look at the condition true column. What's below prints the unique entries in both the training and validation sets. So this is printing the unique values of condition true in order for us to know which type of category it is, I guess, Arduino encoding. If you now write code to fit an Arduino encoder to the training data and then use it to transform both the training and validation data, you get an error. Can you see why this is the case? Because they are not based on frequency and they are based on, you have to use the other method. This is not about most often or less often. Fitting another Arduino encoder to a column in the training data set, data creates a corresponding integer valued label for each unique value that appears in the training data. In the case that the validation data contains values that don't also appear in the training data, the encoder will throw an error. So it is not what I was assuming. Because these values won't have an integer assigned to them. Notice that the condition true column in the validation data column contains these values, but these don't appear in the training data. So it's gonna throw an error because they are different. So this contains this, and this doesn't. Thus, if we try to use an Arduino encoder with scikit-learn, the code will throw an error. So why does this happen? Well, because the way that it was split, because you were splitting the test and the validation set randomly, then they might have different categories. That's why. This is a common problem that you encounter with real world data. And there are many approaches to fixing this issue. For instance, you can write a custom Arduino encoder to deal with the new categories. Simplest approach, however, is to drop the problematic category columns. Run the call cell below to save the problematic columns to a Python list bad label columns. Likewise, columns that can be safely Arduino encoded are stored in good label columns. So it's creating a loop through the xtrain columns, attaching to this variable with the columns that are categorical. Then is looping through the list of the columns. Then is selecting for if set x valid column dot is subset xtrain column. So I think this basically checks if they both have the same values, each one. It's basically a filter for that. And then is subtracting the list of all, the set of all the columns to the set of the good ones and putting on the bad columns. Use the next code cell to Arduino encode the data in xtrain and xvalid. Set the preprocessed data frame to label xtrain. We have provided code below to drop the categorical columns in bad label columns for the dataset. You should Arduino encode the categorical columns in good label columns. So I guess the object is already done, maybe. I don't remember if it's like this. I'm pretty sure it's like this. And then you fit, then you transform the x valid. But let me see if I called it correctly. Yeah, Arno underscore encoder. But I don't remember seeing this being generated on this exercise thing here. So it's probably gonna fail. Gonna test, and if it fails, I'm gonna do the full thing. Yeah. So this creates the object. We transform. Maybe I should put them on the data frame as well. Maybe this is good label columns, not X-ray. Or X-ray. Good label columns. I'm not sure if this is equal to a variable or not. Yeah. Let's see if this works. Columns must be the same length as key. Oh, it's already done here. Yeah, I'm a little bit lost. Maybe, oh, I think I know now. So first you drop, then you make. Columns must be the same way. I have no idea what's wrong here. Maybe I don't need to attach to a variable. Maybe I need to. Maybe that's the thing. Yeah, I have no idea. I'm gonna look at the hints. Use the ordinary encoder class from scikit-learn. You should only encode the columns in good label columns. Yeah, I don't know. I'm lost. I think I'm gonna look at the solution. Maybe I have to do it like it's probably exactly the same way. But I think I already tried this. And it didn't work. Yeah, it says that it isn't the same link. So maybe well, oh I have to make it equal good labels here. That's probably what's wrong. Yes, nice. Because I'm only making the good label columns equal to the transformation. Now it makes sense. So first you drop the bad labels, then you have to select the good labels because you don't want the whole data frame. Because the whole data frame contains numerical values, I think. I think that's the issue there. No, the print MA. So far, if you've tried two different approaches to dealing with categorical variables, and you've seen that encoding categorical data yields better results than removing columns from the dataset. Soon you'll try one-hot encoding. Before then, there's one additional topic we need to cover. Begin by running the next code cell about changes. So I assume this gets unique values of no, but I'm not sure. Lambda calls a function, then column selects the unique values of no unique values of X-string column compared with object columns and maps that to a list. And this code is kind of hard for me to understand. Second part, I think, is creating a dictionary of the object calls. So this, I think this object unique finds the missing values. It loops through the X string columns, find their no unique values, and puts them on the object column, I think. Investigating cardinality. The output above shows for each column with categorical data the number of unique values in the column. For instance, the street column in the training data has 2 unique values, corresponding to a gravel road and a paved road, respectively. We refer to the number of unique entries of a categorical variable as the cardinality of that categorical variable. For instance, the street variable has cardinality 2. Use the output above to answer the questions below. In the line below, how many categorical variables in the training data have cardinality greater than 10? So I'm not sure if I'm supposed to. I think I'm just supposed to count here. But maybe there's a way to code this. I can just create a loop and then use the filter, but I think I'm gonna look at the solution because they just want me to count. And I already understood the concept, so I don't see the need. For large datasets with many rows, one-hot encoding can greatly expand the size of the dataset. For this reason, we typically will only one-hot encode columns with relatively low cardinality. Then, high cardinality columns can either be dropped from the dataset or we can use Arno encoding. As an example, consider a dataset with 10,000 rows and containing one categorical column with 100 unique entries. If this column is replaced with the corresponding one-hot encoding, how many entries are added to the dataset? I think at 10,000 times 100. If we instead replace the column with the ordinal encoding, how many entries are added? Then I think is 100. So 10,000, 10, 100 times 100. And here is 100. I think, not sure. So I did this calculation wrong, but I counted the wrong way. Yeah, but it was what I was thinking. One, two, three, four. Two, three, four. Well, it's the same number. I guess it's the reverse order. That's the problem. What? Four. Yeah, it seems like 10,000 times 100 here. How many entries are added to the data set by replacing the column with a one hot encoding? So maybe it is a different number. If I understand correctly, for each unique entry, you're gonna have 10,000 rows. To calculate how many entries are added to the dataset through the one-hot encoding, begin by calculating how many entries are needed to encode the categorical variable. Multiplying the number of rows by the number of columns in the one-hot encoding. Then, to obtain how many entries are added, the dataset subtract the number of entries in the original column. So it's probably this minus 10,000 minus the number of, yeah, not sure. I'm just gonna look at the answer. Yeah, it's minus 10,000 because it's the ones that are added. Next, you experiment with one-hot encoding, but instead of encoding all of the categorical variables in the dataset, you only create one-hot encoding for columns with cardinality less than 10. Run this code cell below without changes to set low cardinality calls to a Python list containing the columns that will be one-hot encoded. Likewise, high cardinality calls containing this that will be dropped. So it's looping through object calls, selecting less than 10 unique values, and here selecting the list of one minus the other. One hot encoding. Use the next code cell to one hot encode the data next train next valid. Set the preprocessed data frames to echo these names respectively. The full list of categorical columns in the dataset can be found in the Python list object calls. Should only one hot encode the categorical columns in low cardinality columns. All other categorical columns should be dropped from the dataset. Uses many lines of code as you need. So first, I'll make so first I'm dropping the cardinality high cardinality columns. Then I have to create I think I can create the object first. OH encoder, one hot encoder. Then I have to pass the variables there. I think sparse equals false is the second one. The first one, handle unknown equals ignore. Equals ignore. Then PD data frame. Uh, encoder dot fit transform. Low drops. Low drops. Right. The same here for the validation. And here just transform. Let's see. Not found in access. Hmm. So maybe I need to do some sort of loop like this. Full list of categorical columns in the dataset can be found in the Python list object calls. So maybe it's just object calls for both of them. So maybe it's just the one hot encoding. And I don't need to do the first step. This thing right here. I think this is X string. Yeah, X train, valid. That's what I forgot. So maybe the other stuff was correct, but I forgot to put X valid in X train. Let me try the other way. Yeah, I think I'm gonna have to look at the solution here. Also, I need to do stuff after. Oh, I forgot about the putting the index. So I think this part is correct. Which calls? Yeah, it's written differently here, but I guess it's the same thing. Then is making a variable with the removed categorical from the original data frame. Then it's gonna concatenate both of them. It's pretty much impossible for me to remember this. At first try. There's too many stuff, Joe. Too many steps to remember. I think I'm getting the rough idea of the logic. Generate test predictions and submit your results. After you complete step 4, if you'd like to use what you've learned to submit your results to the leaderboard, you need to pre-process the test data before generating predictions. These steps completely optional and do not need to submit those to the leaderboard to successfully complete this exercise. So I'm gonna run everything and save. And these are the same steps as before to input to submit the thing, which I'm not gonna do. So far, I found dealing with the categorical variables the most annoying part of the most confusing and annoying part of the thing of machine learning. If you use libraries to build the models, because building the models is also very difficult. Missing values, missing value handling, categorical encoding, your modeling process is getting complex. This complexity gets worse when you want to save your model choose in the future. The key to managing this complexity is something called pipelines. Learn choose pipelines to reprocess data. So I guess this is the next step. Yeah. I think I'm gonna stop here for now. See how long. Almost 2 hours. I think it's better to stop here. So next time I'm gonna have roughly the same amount of time that I spent today to finish. Then I will. So I'm gonna reset the stream and start watching the. I'm gonna go eat something and upload this part of the video, this video, and then I'm gonna come back and start watching this relatively playlist to finish today. So see you.